Hello everyone, welcome back. We are in the fifth lecture of week one of this course, Reinforced Concrete Design. And you have seen how the working stress method works. And we have also discussed the advantage and disadvantage of working stress method. And for that reason, we need to evolve with the design philosophy. And now we have what is called limit state method. In fact, in the previous lecture, we discussed what is the disadvantage of working stress method, and then we said that loads are of different nature and they have uncertainty, inherent uncertainty, and the level of uncertainty is different from one type to another type. So, this method, limit state method, it addresses both ultimate strength and serviceability requirement of a structure satisfactorily. So we have different limit states. What are the different limit state? Limit state of collapse and then limit state of serviceability. Now, when we design a structure, for example, if you consider a beam which bends and, for example, say take a simply supported beam with a point load at the middle, then all of you can draw the bending moment and shear force diagram. So we need to design against bending, against shear. Likewise, maybe other structure encountering some kind of torsional force. So you need to design it against torsion. So this limit state of collapse, these are basically the performance function that takes care of those flexural requirement, shear requirement, torsional requirement, and maybe other where you have a combination of these. So we have different limit state which are primarily different performance function. Some limits we define, crossing of that limit, we call it a failure. Okay, so when we talk about ultimate strength, we define this limit state of collapse. And then when we talk about serviceability, that means a structure can be safe, but when we apply the external loading, it can have excessive deformation. Then that is not desirable, and in that case we have the serviceability requirements where we specify the deflection or the amount of crack that we allow to develop. So these are the requirements. They again offer us some performance function that comes under the serviceability requirement, and for that also we have some dedicated limit state. As we progress in the design, we will see how we define these limit state of collapse and limit state of serviceability. Sorry, here it will be serviceability. Now for all these limit states, first what we need to define is characteristic strength of the material. Again, we have concrete and we have steel. So we need to define characteristic strength. It is that value of the strength below which not more than minimum acceptable percentage of the test results are allowed to fall. For example, if you take the definition of FCK values as per IS 456, if you recall, we discussed that 5% of the values are allowed to fall below the specified limit, right? So normally we consider 5% as the limit, and that is recommended even in Indian code. So if we test samples, say for example concrete, then if we plot the frequency of the test results of different, say, stress, here say F, material property. So we have this type of distribution. Now the middlemost value here, it is the mean value. So this is Fm. So you allow only 5%. So this area, this is 5%. And this value here is actually the Fk, we call it Fk. So Fk, that is the characteristic value, is equal to Fm minus some constant times Sd. Sd is the standard deviation. So if we have a number of tests, we can find out mean, we can find out standard deviation. And if it follows normal distributions, k is 1.65 approximately. So we have Fm minus 1.65 times Sd. So that is Fk. Now if it is concrete, obviously we have Fck, and if it is steel, we have Fy. These are the Fk values, right? And then once we find out this Fk value, next what we have to do in this design philosophy, we have to find out what is Fd. That is the value we use in design. For that, what we do, we divide Fk with a partial safety factor for material. So that is what we call gamma m. So first we find out Fk, that is the characteristic value. Then we use appropriate partial safety factor to reduce it, and then we have the design strength of the material. So this is the design strength of the material. And code specifies that gamma m is equal to 1.5 for concrete and 1.15 for steel. Because steel comes from a batch production with better quality control, material partial safety factor is less in case of steel compared to concrete, which is produced at site, and hence there are chances of more uncertainty compared to steel, and that's the reason we have a bigger value of gamma m, that is the partial safety factor for material. So there are two major steps. What we have to do, we first have to find out the statistical variation of the material property. Based on that, we have to find out what is the mean value, and we have to find out the standard deviation. And using these two properties, we have to first find out what is the characteristic strength. And the moment we find out characteristic strength, we further reduce it by this material partial safety factor to get the design strength of the material. So that is the first step. Next is characteristic load. Just like in case of material, we have uncertainty. That means, again, if we take the example of concrete, if we take the samples of concrete from the same batching plant at the same moment, from the same mix design, and if you cure it for 28 days, then if you test it, you will see there is a variation. And that's because of uncertainty. Likewise, in case of load also, it is having some uncertainty. And in case of load, it is that value corresponding to 95% probability, which is we consider the characteristic load. That means again 5% of the load is allowed to fall above this specified value. Okay, so if we plot the frequency versus the load value, which is say L here, so what we have here is something like this. And here, this area on the right hand side, this is again 5%. So we have the mean here, Lm, and this is the value of Lk. And this value is K times SD. So in case of load, we have Lk is equal to Lm plus K times SD. Sometimes we also write capital Fk is equal to Fm plus K SD. SD is the standard deviation associated with that particular type of load. It may be dead load, it may be live load, it may be any other type of load acting on the structure. So when we start the design, first we define the characteristic strength of the material for both concrete and steel, and then we go to load, and we have different types of load acting. For example, dead load of the structure, which is the weight of the structure. Then a live load, that means if it is a school building, the school students coming within the classroom, so that is the live load. Likewise, if it is an office building, if it is any other, if it is a theater, so we have different values of live load, different types of live load also acting. Then we have many other loads. For example, if we have a building housing some equipment, so we have a dedicated superimposed dead load. Likewise, there may be thermal load. So all these loads, they have separate uncertainty features that comes from actual data dealing with that load. So from that actual experiment, we can collect the load value, and we can find out the variations within that load value. That tells us what is the mean and what is the standard deviation. And once we can find out the characteristic load. Now, obviously, if we deal with a very special type of loading, we need to go for a full-scale experiment. And then from that experimental results, we need to find out all these variations, the uncertainty associated with that type of loading. But not always it is possible to go for experimental investigation of different types of load. And that's the reason we have in our codal provisions different values of characteristic values of load specified in our codes. For example, dead load is specified in IS 456. Likewise, we have live load also specified there. Then we have wind load in a different code, earthquake in another code. So we have dedicated codes for different types of loading. When those loads will come, we'll update you how to deal with those codal provisions. But for the time being, the fact to be noted here is that we have to find out this characteristic load and then use that characteristic load in your design. Right. Okay. Now, once these two parameters are defined, that means the material strength and load, then what we have to consider is the stress strain behavior. Now, we have two different materials here, concrete and steel. So for concrete, if we plot the stress strain curve, let me just once more draw it. So we have on the x-axis, we have strain, and y-axis we have stress. Now, if we plot this, we get this is the actual behavior of stress strain curve. Now, let us first define the strain values. So this is 0.001, this is 0.002, and then we have here 0.003, 3, and somewhere here this value is 0.0035. So this is the actual stress strain behavior. Now our code says you can idealize this behavior using this line. So initially we have a parabolic profile. So this is parabolic. Then corresponding to 0.002, that is 0.2% strain, the value we have, beyond that it reduces, but code says you can consider this idealized curve. Let me redraw with a different color. So beyond this point, you just go like this, a straight line. And this is idealized stress strain curve. So this value, if I project it back here, is what is called the FCK value. Again, I repeat, corresponding to 0.2% strain, the value we have. Beyond that, on the right hand side, it is horizontal. That is the idealized curve prescribed by code, and then that value is basically the FCK value. Now what we do, we then apply the first factor, and then this value we get, and this is nothing but FCK divided by 1.5, and then what we get is 0.67 FCK. I'll explain that in a minute. And then finally what we do, we apply then partial safety factor for this material. So what we'll get is this value and then idealized one here. So this value is 0.67 FCK divided by gamma m. Recall gamma m is 1.5. So if I divide it 0.67 by 1.5, we get 0.446 FCK, and up to 2 decimal place it is 0.45 FCK. So this is the design value we will use for concrete. Now the question is, why we have this first factor? The reason is, when we check the compressive strength of concrete, what we do, we take some samples and we make a cube, right? And then in the actual structure, we have the concrete strain that we measure using a concrete cube. Because of this size effect, there may be a variation from the test results that we have to the actual structure. And because of that reason, to deal with that reason, that size effect, we apply this factor first. Okay, and then we apply gamma m as per Codal recommendations. So the point to be noted here, the stress strain behavior of concrete, which is not initially straight, these curves are all parabolic. Okay, these curves are parabolic curve, but corresponding to 0.2% strain, we consider the value of FCK, but we idealize the actual curve as per Codal recommendations. So first we consider the size effect, we reduce this FCK value, and then we apply a partial safety factor to reduce it further. And then we finally get the design strength of concrete that we are going to use. Now let us quickly see the steel. For steel, as you can see on your screen, the stress strain behavior of steel is a typical stress strain behavior is shown here. Initial part is again straight line. Then we have a small nonlinear behavior. Then we have a valley portion, and then again it increases because of various other reasons. For the timing, we are not going into the details of that. Concrete is a brittle material and this steel is a ductile material, and that's why beyond this point of yielding, it still has large range of strain before ultimately it fails here at the extreme right end. Obviously, we will not go into this part. This part is not required for the time being. So, we have this behavior from say initial 0 to up to B. We have this behavior initially straight line, and then there is a small curve, and then almost it becomes horizontal. So, if we go up to C, it is initially straight, then small curve, and then becomes horizontal. Now, that curve is again idealized by code. What code says is that you consider initial linear variation, and then the moment it yields, you just consider that flat point. So this is strain, and on the y-axis we have stress. So we started with this original behavior, and then again here in this case we have this idealized behavior. So we have this value is what is called the characteristic value, or Fy, or where we have yielding. Then code says you apply a material factor, effectively you reduce it. So this is your Fy value, and then you apply Fy by gamma m, and in this case we have gamma m is 1.15. So effectively this value we have 0.87 Fy. So that's the FD design value that we are going to use. So these are the two different ideal stress strain behavior that we'll use in our limit state method of design. And as we progress, we'll see now we'll consider first the same singly reinforced section, and with this variation of strain and stress, how we can model first the location of the neutral axis, then again we'll define the critical section, and based on the actual location of the neutral axis above or below, we'll define under reinforced or over reinforced section, and for every case how we can find out the sectional moment of resistance. That will be the capacity of that particular section, and we have to design it in such a way that the capacity is more than the demand, and then our design will be safe. So that we will do with this background of stress strain behavior in our next class, and we'll see how we can design beam sections using limit state method. Thank you.